Now let's talk about reversible additions of amines to ketones and aldehydes. Ketones and aldehydes add to amines, or rather amines add to ketones or aldehydes to form imines, sometimes called Schiff bases, but imine is much better. Again, much like acetals, this equilibrium usually favors the left by quite a bit, but if we remove water as it's formed, we can push the equilibrium to the right. Okay, so generally speaking, we're going to want to remove water as we do this. Not always, but if we have a hard time making it, that's one way to do it. Let's go through the mechanism of this reaction. It turns out the maximum rate for this reaction is a little bit acidic, but not too acidic. So pH 4 to 6, just on the acidic end of the pH scale. We can start off by having amine act as a nucleophile. Now usually we don't like intermediates where we have a positive and a negative charge. But in this case we can make an exception because nitrogen isn't that electronegative, so N plus is relatively stable and O minus is relatively stable. So this is, usually we don't like plus and minus together, but this is a reasonable intermediate. Right, but it will be in equilibrium with the neutral version of it, right? So if this hydrogen gets passed from this nitrogen to this oxygen, either directly or through some solvent molecule intermediary, whatever. Once we get to this tetrahedral intermediate, again, most of the time we will simply protonate, add nitrogen and kind of walk backward. But once in a while, we'll protonate on oxygen instead. Now, I want to be clear about this. This is many, many thousands of times more likely to go this way than that way, right? The order of magnitude of the basicities of this is, this is a good base. This is not a great base at all. But one time in a blue moon, yes, we will protonate at oxygen, and as soon as we do, we can lose water. And if we lose water and we don't give it back, then that's our handle on pushing the equilibrium to the right. Once this is water, I just have this conjugate acid of an imine, an iminium ion, I guess, that then is going to lose that acid proton to get to that. So this is an imine. This is the mechanism by which it's formed. Slightly acidic helps us out. So again, we can go through why do we need acid? We need acid because we need to protonate this OH, right? This is an unlikely intermediate anyway, but if it's not acidic, this becomes very, very, very unlikely, right? So we need a little bit of acid. But we can't have too much acid. If we have too much acid, then all of our nucleophile is going to be sucked away as NH3+, right? That's not nucleophilic anymore. So we can't have it at pH 1 or 0 because then we don't have a nucleophile anymore. But we can't have it at pH 10 or 12 because then we'll never lose water. So we're looking for that happy medium. Let me jump to PowerPoint for a second to talk about some important reactions of imines in biochemistry, particularly biosynthesis. So transamination is an important biological process. It's part of how your body synthesizes phenylalanine and how it synthesizes lots of neurotransmitters as well. Inside the enzyme catalyst, we've got our carbonyl substrate here on top, and we've got our amine that's part of pyridoxamine phosphate. So this is a coenzyme, so or a cofactor. It's a small molecule that fits into an enzyme. You might have heard of NAD. This is kind of like that. When we talk about vitamin B6, this is considered a B vitamin. And this forms an imine in situ. So the NH2 condenses or reacts with the CO double bond, and we lose water and end up with this imine. Now, here's the cool part. Enzymes aren't magic. Enzymes just kind of have acids and acidic sites and basic sites at kind of the perfect spot to help a reaction go. This particular enzyme has a basic amine from, I think lysine is the amino acid, has a basic amine in exactly the right spot to grab this kind of acidic proton. And this is acidic because of this NH plus way down here. So as this gets plucked, now I have this fully conjugated system, lone pair all the way up, all the way conjugated. Is this reversible? It is reversible, but I can now put that proton back either here, or I can put it back on a different carbon. As we hydrolyze that imine, again remember, amines plus water go to amines and ketones. That gives us new products, right? So this used to be a CO double bond. This used to be an NH2. They've changed partners. Now I have phenylalanine, one of the 20 canonical amino acids, and I have PLP, pyridoxal phosphate, which is now going to cycle back to pyridoxamine by doing this reaction somewhere else in reverse. This transaminase is exactly what it sounds like. It's trans is across. It's sharing amines sort of across from one molecule to another. But the way it does that is by the kind of equilibrium between these two imine intermediates. So imines, very important biologically, and also not just in transaminases, but in racemases and also decarboxylases as well. What can these imines be used for? So synthetically, there are some drugs that are imines. Benzodiazepines are all imines and are made by the cyclization of a carbonyl compound with an amine. So that's a really important example. But often, imines are used to get to amines by a process called reductive amination. So the idea here is that I'm starting with a ketone or aldehyde. I'm making the imine by bringing those two things together, and then I'm reducing that imine down. So I can reduce it with sodium borohydride. That's going to reduce a CN double bond just like it reduces a CO double bond. So imines are about as reactive as ketones or aldehydes. So it's easy for sodium borohydride to add hydrogen here, and then upon aqueous workup, the hydrogen gets added there. So I essentially reduce this the same way that I would reduce a ketone or aldehyde. If you want to get really fancy, you can do this in one step with something called sodium cyanoborohydride. And this is almost like the Lindlar catalyst we learned about earlier, where we're making catalyst better by making it bad. So we're taking our nucleophile, BH4, and we're adding a strong electron withdrawing group to it. And so now, this is now a really lazy nucleophile. This isn't going to react with aldehydes and ketones anymore, which is good because I don't want it to react with this ketone. It'll wait. It'll be sleeping in the corner until the very end of the imine mechanism where we get this iminium ion. And once I get that iminium ion, that and only that are reactive enough for sodium borohydride or cyanoborohydride to react with. So again, if you like to memorize stuff, or if you think synthesis is super cool, you can use sodium cyanoborohydride to do this in one step. But it's okay to think about this in two steps, right? I can get to an amine from a ketone or aldehyde in two steps. First make the imine, removing water, then reduce it with sodium borohydride.